welcome to another module in this massive open online course. So, today let us start looking at the frequency domain representation of signals, alright. So, today we will start looking at what is known as and what you must be familiar with to some extent, the frequency domain representation of signals. So, we are going to look at the frequency domain representation, all right, and this is one of the fundamental tools in communication. The frequency domain representation is one of the fundamental tools available This is one of the fundamental tools required or one of the fundamental tools used in communication, and this frequency domain representation of the signal is termed as the spectrum of the signal. So, this is termed as the frequency domain signal representation is termed as the spectrum, right, the spectrum of the signal. And further, this spectrum can be of two types. One is we can have a Fourier series which is discrete in frequency, this Fourier series is discrete in frequency, and the other representation is the Fourier transform. And this Fourier transform, this is continuous. This is continuous. So, we have the Fourier series which is discrete, the Fourier transform which is continuous in frequency. So, we have these two different kinds of course, we have more kinds of signal or spectrum or frequency domain representations, but for the purpose of this particular course, these two are going to be sufficient. One is the Fourier series which is discrete in frequency, we are going to look at it in greater detail, and the other is the Fourier transform which is continuous in the frequency domain. First, let us start looking at the Fourier series representation. Okay. So, we start by looking at the Fourier, let us start by looking at the Fourier series, and the Fourier series is defined, it is important to remember this is defined for a periodic signal. This is defined for a periodic signal xt. So, let us consider xt to be a periodic signal. So, consider xt to be a periodic signal with period capital T, all right. So, xt is a periodic signal, all right, we are all familiar with the notion of a periodic signal. So, consider xt to be a periodic signal with period capital T. Okay. Now, the Fourier series of xt is given as the Fourier series of x t is given as x t, this is given as, let us write this down, x of t equals summation k equals minus infinity to infinity. So, let me just write it a bit more clearly. This is summation k equal to minus infinity to infinity c k e to the power of j 2 pi k f naught t, where f naught equals 1 over the time period. Remember, capital T, this is the time period of the periodic signal. F naught equals 1 over the t, this is termed as the fundamental frequency. F naught is the fundamental frequency of periodic signal f naught is the fundamental frequency of the periodic signal x of t, okay. And this is the Fourier series representation, correct, c k e to the power summation c k e to the power of j 2 pi k f naught t, and this quantity c k is the kth Fourier series coefficient. This quantity c k, all right, the summation c k e to the power of j 2 pi k f naught t. F naught is the fundamental frequency, which is 1 over capital T, where T is the time period of the periodic signal, and f naught is the fundamental frequency, right, and c k is the kth discrete Fourier series coefficient of this periodic signal x k. Okay. And now look at this, now let us try to understand this a little bit better. If you look at this quantity e to the power of j 2 pi k f naught t, look at this quantity e to the power of j two pi k f naught of t, this is equal to cosine e to the power of j theta is cosine theta plus j sin theta. So, this is cosine 2 pi k f naught t plus j sin 2 power k f naught t. This is also this is basically a complex sinusoid. Correct. Remember, we said cosines and sines are sinusoids. So, cosine 2 pi k f naught t plus j sin 2 pi k f naught t is a complex sinusoid. So, what we are saying is, if you can look at this, the summation c k e to the power of j 2 pi k f naught t is basically nothing but a linear combination of sinusoids at the fundamental frequency f naught and multiples k f naught of the fundamental frequency. All right. So, what we are saying is, if you can look at it, each k f naught is each k f naught equals a multiple of fundamental. This is a multiple of the fundamental frequency f naught, the kth multiple of the fundamental frequency f naught, correct. So, summation c k e to the power of j 2 pi k f naught t is basically nothing but a linear combination of these various complex sinusoids at either frequency f naught or k f naught. K f naught is basically a multiple of the fundamental frequency f naught. So, this is a linear combination. So, what we are saying is, every periodic signal x t with period with fundamental frequency f naught can be expressed as an infinite, as a linear combination of an infinite number of sinusoids at either the fundamental frequency f naught or an integer multiple of the fundamental frequency f naught, that is at k f naught, alright, and that is the power, or that is the intuitive explanation of this discrete Fourier of the discrete Fourier series expansion of a periodic signal x t. Okay. And this sinusoid at k f naught, that is this sinusoid at k f naught, that is e to the power of j 2 pi k f naught, correct. This sinusoid that is sinusoid at integer multiple of f naught t, this is termed as the kth harmonic, and Ck is basically the coefficient of the kth harmonic in the linear combination. So, Ck is the coefficient of the kth. So, e to the power of j 2 pi k f naught is k f naught t is the kth harmonic, correct, which is associated the kth multiple of the fundamental frequency f naught, and Ck is the discrete Fourier series coefficient associated with the kth harmonic in this discrete Fourier series expansion. Okay. Now, let us look at how to find out the coefficient Ck in the discrete Fourier series. Okay. So, let us now look at coefficients how to find the coefficient Ck of the discrete Fourier series. Let us try to make it Cl, since we are already using k as the index of the discrete Fourier series. Now, we will show, let us consider this quantity integral 1 over t minus infinity to t x of t e to the power of j minus j 2 pi L f naught t. We will show that this quantity, this integral here boils down to yield the Lth coefficient Cl of the discrete Fourier series. For that, what I am going to do is I am going to substitute the expansion minus infinity to infinity summation, I am sorry, this integral is over one period. So, that is from minus t over 2 to capital T over 2 minus t over 2 minus t over 2 to t over 2 summation k equal to minus infinity to infinity Ck e to the power of j 2 pi k f naught t, correct, multiplied by e to the power of minus j 2 pi, has to be a dt e to the power of minus j 2 pi L f naught t times dt. Now, interchange the summation and integration, that is interchange summation and, or rather interchange order of summation and integration, and that yields, take the summation outside, that gives k equal to minus infinity to infinity, correct, Ck times 1 over t integral minus t by 2 to t by 2 e to the power of j 2 pi k minus L f naught t dt. Now, let us look at this integral 1 over t integral minus t by 2 to t by 2 e to the power of j 2 pi k minus L f naught t. Let us look at this integral. Let us try to infer the properties, or let us try to find out the properties of this integral, and we will see this as a very interesting property. That is, let us look at this integral 1 over t integral minus t by 2 to t by 2 e to the power of j 2 pi k minus L f naught t. Now, if k equals L, then e to the power of k minus L equals 0. So, e to the power of j 2 pi k minus L f naught t, that is e to the power of 0, that is 1. So, this integral becomes, so this integral, if k equals L, this integral becomes integral 1 over t minus t by 2 to t by 2 1 times dt, which is 1 over t times t. So, this is 1. So, what we are saying is, if k is equal to L, then 1 over t integral minus t over 2 to t over 2 e to the power of j 2 pi k minus L f naught t dt is 1. Now, if k is not equal to L, now if k is not equal to L, that is k minus L is not equal to 0, then this integral becomes 1 over t. Well, let me just write this on again, minus t by 2 to t by 2 e to the power of j 2 pi k minus L f naught t dt. So, k minus L is not equal to 0, which means I can now evaluate this integral as 1 over t e to the power of j 2 pi k minus L f naught t divided by j 2 pi k minus L f naught between the limits minus t by 2 to t by 2, which is equal to 1 over t 1 over j 2 pi k minus L f naught. Now, e to the power of j 2 pi k minus L f naught t evaluated at capital T by 2 using the property, use property. Remember, we have to use the property f naught equals 1 by t, which implies f naught t equals 1. So, using this property, this becomes e to the power of j 2 pi k minus L f naught into t by 2, f naught t is 1. So, this becomes pi k minus L minus e to the power of minus j pi, at minus t by 2 it becomes e to the power of minus j pi k minus L. Now, look at this, this is a sinusoid evaluated at phase pi k minus L and phase minus pi k minus L. The difference between the two phases is 2 pi times k minus L, that is integer multiple of 2 pi. Therefore, these two complex sinusoids are equal, hence the difference is 0. So, phase difference equals 2 pi k minus L, which means this quantity here, this is equal to 0. Therefore, if k is not equal to L, therefore, to summarize, if k is not equal to L, then 1 over t integral minus t by 2 to t by 2 e to the power of j 2 pi k minus L f naught t is equal to 0. Okay. So, what we have shown is that this quantity 1 over t integral minus t by 2 to t by 2 e to the power of j 2 pi k minus L f naught t dt f naught t dt, this is equal to 1 if k is equal to L 0, if 1 I am sorry 1 if k equal to L, 0 if k for all integers k not equal to L, this is 0. Okay. So, and this is an incredible property, that is, if you can look at this, this shows nothing but the fact that these different harmonics e to the power of j 2 pi k f naught t e to the power of j 2 pi L f naught t, these are orthogonal. The different harmonics, the kth harmonic and lth harmonic these different harmonics, that is e to the power of j 2 pi k f naught t e to the power of j 2 pi L f naught t, when k is not equal, these different harmonics, the different harmonics, right, at different multiples of f naught, k f naught and L f naught are orthogonal. That is why you have integral minus 1 over t integral minus t over 2 to t over 2 e to the power of j 2 pi k f naught t times e to the power of j 2 pi L f naught t conjugate, that is e to the power of minus j 2 pi L f naught t dt, that is equal to 0. That is property. Let me just write it again clearly to illustrate the orthogonality. We say x t and y t are orthogonal if this dot product or the inner product minus 1 over t minus t by 2 x t into y conjugate t dt is equal to 0. Here we have integral minus t over 2 to t over 2 1 over 2 1 over t e to the power of j 2 pi k f naught t times e to the power of minus j times e to the power of j 2 pi L f naught t conjugate into dt equals 0, hence these two are in fact this is a very important property, these two are, that is the different harmonics, harmonics at k f naught, harmonics at L f naught, these two are the kth harmonic and the Lth harmonic are orthogonal. And we will now use this property to evaluate Ck as Cl, and that can be simply shown as follows. Because look at this, if you go back here, this integral, all right, let us go back to this integral, that is summation, we have shown that 1 over t integral minus t over 2 to t over 2 x t e to the power of minus j 2 pi L f naught t dt, this is equal to summation k equals minus infinity to infinity C k times 1 over t integral minus t by 2 to t by 2 e to the power of j 2 pi k minus L f naught t dt. This integral is non-zero, this integral is 0 if this integral is 0 if k not equal to L 1, if k k equal to L. So, it is going to survive only when k equal to L. So, this only the term corresponding to CL is going to remain, and therefore, this is simply equal to, you can also write this as summation k equal to minus infinity to infinity C k delta k minus L, because this is a delta function where delta of 0 is 1 and delta of any other integer n is 0 if n is not equal to 0, that is basically, therefore, this is basically simply equal to your C L. Okay. So, what we have is basically that, completing this we have integral x t e to the power of minus j 2 pi L f naught equals C L. That is the coefficient of the, where C L is coefficient of nth harmonic or nth coefficient in discrete Fourier series representation of x t, or the nth coefficient in the discrete Fourier nth coefficient in the discrete Fourier series representation of x t, or rather let us characterize this, or let us qualify this as a periodic signal x of the representation of the periodic signal x t, correct, nth coefficient in the discrete Fourier series representation of the periodic signal x t. So, what we have done so far is, what we have done in this module is basically we have started to look at the Fourier domain or frequency domain representation of the signal x t, looked at the Fourier discrete Fourier series representation of a periodic signal x t. We said that any periodic signal x t can be represented as with fundamental frequency f naught, where f naught equals 1 over t, where capital T is the period of the signal, can be represented as the summation or the linear combination of an infinite number of complex sinusoids at the fundamental frequency f naught and multiples of the fundamental frequency, that is k f naught, that is the sinusoid corresponding to the complex sinusoid corresponding to the fundamental frequency f naught and its various harmonics, correct. And we have also shown how to compute the discrete Fourier series coefficient C k corresponding to kth harmonic in this discrete Fourier series representation. So, we will stop this module here and continue with other aspects in the subsequent modules. Thank you very much.